This session is entitled STRec, which is a sparse transformer for sequence recommendation. And this is presented by an author. Kwai Dong Lee is here. Kwai Dong, the floor is yours.
Yes. Hello everyone, good afternoon. This is Qidong from Xi'an Jiaotong University and the City University of Hong Kong. Here I will introduce our work STRec, sparse transformers for sequential recommendations. And this is the outline of my talk. I will first talk about the background and the motivation of our work, and then the proposed framework and the experiments will be detailed. And as we know, the recommender systems become important in our life because it can select and suggest relevant information to us. For example, we can say this when we face with a large amount of movies, we may be confused to select which one. And at this time, the RS can give us a proper movie, which means that it can help us to elevate the problem of information overload. And recently, sequential recommendation becomes popular since it can recommend items based on the user's behavior history. Still take the movie recommendation as an example. The SRS gives us the next movie recommendation according to our watching history as. And the key of SRS is to extract user preference from the sequential interactions. And then I refer to the motivation of our paper. As we know, the transformer is widely used in SRS to capture users' preference. However, the vanilla self-attention often computes the attention scores between every atom pair. Such operation will cause the following two challenges. The first one is the huge computation, which may cause huge time and memory costs in online services, which is difficult to be accepted. And the second one is that such RS model may take the suboptimal atom interactions into account, which may degrade the recommending performance. And to further explore such a problem, we first conduct preliminary experiments to find out two phenomena. We can say the first experiment, we train a transformer-based SRS model and visualize the attention matrix of one transformer layer, as the red figure shows. And in this figure, the darker green block means the large value. And from the result, we can say the most of interactions has the small attention values. And we can name this phenomenon as the sparse attention phenomenon. And besides, the attention weights vector are similar. You can see the rectangular set. And these two vectors are similar. And this turns out the sparse phenomenon further. And the other experiment, we conducted the SVD decomposition over the attention matrix and plot the distribution of the aging values. And you can see the red figure. The x-axis is the value of aging values, and the y-axis represents the ratio of value. According to the curve, we can show that most aging values are small. And we can call this as a low-rank phenomenon. Such phenomenon illustrates that the attention matrix can be approximated by a low-rank matrix. And motivated by these two phenomena, we propose a sparse transformer as a transformer for SRS, which can only consider the vital interactions. And after the introduction, I will detail our proposed framework. At the first of this section, let's see the overview of our STRec. Similar to the other transformer-based SRS model, our STRec consists of embedding layer, stacked transformer layers, and prediction layer with cross-entropy loss. And the difference is that we substitute the vanilla soft attention layer by our sparse transformer layer. And then the key contribution of our work is the sparse transformer layer. The proposed transformer layer contains a cross-attention mechanism, as the framework shows. And the cross-attention aims to calculate the attention scores for the vital interactions and in avoid of the redundant computation. Thus, it can shrink the complexity. And for the cross-attention mechanism, the key is how to get the relevant and important atom interactions. Here, we propose a novel sampling strategy to get the important atom index from the user interaction sequence, which is based on the time interval. And next, I will detail the cross-attention mechanism and the novel sampling strategy. And you can see in the cross-attention mechanism, we save the time and computation cost by calculating vital interactions only. And so we first sample the vital atoms as the query by the proposed sampling strategy. And then we consider the original sequence as a key and value. And so you can see the derived cross-attention can be written as this formula, where HI is the sampled sequence. For example, in the diagram, atoms with ID 3, 2, and 5 are sampled, and the outer sequence wave H has the same length of the HI. And next, similar to the original transformer layer, FN is adopted, but it takes the shortened sequence wave H as the input. So the output sequence has the same length of the wave H. And due to the shortened input sequence, the complexity gets compressed. If we assume the length, sampled length as the KL, then the computation is changed, complexity is changed from the big O(n) squared to the big O(n) times KL. And then another core of STRec is device sampling strategy. The previous works have proved that the time interval plays an important role in sequential recommendation. And therefore, we use the time interval rather than the order to get the sampling index. As this formula shows, we map the time interval T to the sampling density by an MLP and add a random matrix R from the uniform distribution. However, there are two challenges here. First, if we conduct such operation in every layer, it is time-consuming. And besides, the top K operation is indifferentiable during the training. To face with the first challenger, we only calculate the index rank as the first layer during the inference. And to handle the indifferential problem, we replace the top K operation by the Gamble softmax. Here we calculate a mask matrix to decide which pair of atoms should be considered. And that is when MIG is 0, we will ignore the atom interaction between atom I and atom J. And as for how to get this matrix M, we first use this formula to get the vector S, which represents the vital atom in this layer. And the alpha L in this formula controls how many atoms are sampled in this layer. And then calculate the M by the outer product between the vector SL-1 and SL. And since we use the Gumball softmax to replace the top K operation in sampling, we design a two-stage optimization. At first, we partition the parameters into two parts. The first is for sequential recommendation model, W, and the other is for the sampling. And we optimize all parameters in the pre-training stage. And the sampling is implemented by the Gumball softmax at this stage. And at the fine-tuning stage, we only train the parameters for SRS, and the sampling is conducted by the top K operation. And next, I will introduce the experiment part to show the performance of our STRec. In the experiments, we use the following three data sets: Muillens, Koala, and Amazon. And to evaluate the recommending performance, we use the hit rate, MR, and NDCG metrics. And we also evaluate the inference time and memory cost to prove our work is also efficient. And then I will show these four parts four parts of the experiments. We show the over-recommending performance here. In this table, we can find that transformer-based methods perform better than traditional SRS model. Of course, this phenomenon illustrates self-attention can owns the outstanding ability in modeling sequence. And then we compare with FDSA without set information for a fair comparison, but dropping set information causes its inferior performance. And all transformer-based baselines adopt the vanilla software attention, but they perform poorer than our STRec. This result shows the dropping redundant atom interactions can help us elevate the recommending performance. And besides, it was noting that the TSR-STRec and STRec often can surpass other baselines. We guess that because the effectiveness of introducing temporal information to SRS. Next, to further validate the efficiency of the proposed STRec, we also compare our model with some efficient transformer baselines. We found that the lymphomer and the informer perform much better in memory cost, but their inference time is relatively long. The reason is that they shorten the length of sequence by downsampling, but conduct such operation in every layer. And the reformer, flash, and autoformer perform poorer than both on accuracy and efficiency. The reformer and the flash are designed for NLP tasks whose sequences are relatively longer than sequential recognition. And the autoformer is designed for time series prediction, which involves much conductive bias. In contrast, our STRec outperforms other baselines due to the proposed efficient sampling strategy. And then we explore how the sparsity setting affects the accuracy and the efficiency. From these two figures, we can conclude that the STRec can elevate the efficiency consistently, and if we have too much sparsity, some loss of vital interaction may downgrade our model. For the ablation study, we explore the effectiveness of the proposed sampling strategy. We compare with the three variants of our model. The first samples the top K actions without a random matrix, and the second one samples the actions randomly, and the third one sample based on position instead of the time interval. According to the results, we can conclude that the time interval can better indicate the important interactions. And besides, our STRec outperform STRec 1, which demonstrates that the certain randomness can better indicate the vital interaction. At last, I will conclude our work. First, we identify the sparse phenomenon of existing transformer-based architectures for SRS tasks. And then, based on this phenomenon, we propose an efficient and effective STRec model. And by the experiments, we found the proposed STRec could perform well on both accuracy and efficiency. And that's all of my talk. If you have any questions, please feel free to ask or email to us. Thank you.
Thank you. Thank you. Do we have questions for the author? I see somebody running to a microphone.
Yeah.
Could you say your name?
So yeah, my name is Alexander Petrov. Thank you for presentation. So one of the motivation slides was showing us SVD composition of the attention matrix. And can you please explain what does it really mean that attention matrix has slow rank? And is it good or bad, or how can we interpret this? And second, is your motivation more about effectiveness or efficiency of the model?
Okay. Thanks for your question. Actually, our motivation is from the sparse transformer. And these works are mainly in NLP tasks, and they do some primary experiments like us to show the eigenvalues of the transformer of the attention matrix is sparse. And in my opinion, the low rank means that only most of the values in the attention matrix is approximate the zero. And so such sparse matrix can be approximated by small matrix, like the, you may say the LLM is popular, you may know the LoRa. This idea may be similar to that one. We can use low dimension matrix to approximate the original big matrix. And so we proposed our sparse transformer for SRS. And actually, we may see many works in NLP and move them into our recommendation work. Yes.
Okay. Thank you.
Thank you.
Hi. Thanks for the nice talk. So my question is that sparse attention mechanisms have existed for a while in different applications, like the approaches that take the computation from n squared to n square root n. So what is the key differentiator for your work in applying it to the recommendation space? Is it the sampling strategy, or?
Okay. Maybe I understand your question. Maybe how our STRec may be applied to the real-world applications.
No, I mean, how does it differ from existing sparse attention mechanisms?
Okay. Maybe this is similar to the last question. Our work actually is from the NLP task, and you refer to the sparse transformer. This works all in the NLP task, and our difference is that we use the time interval to sample the vital interactions, not only the order you may know many efficient transformer only use the orders to sample the interactions, maybe long-former, informer. They use the near interaction, near atoms, or use the random atoms. But we apply the time interval, which may be more suitable for the sequential recommendation task. And I think this is a main difference.
Okay, thanks. So it's mainly in the sampling strategy difference to adapt it for recommendations?
Yes, yes.
Okay,
Thanks.
There was a similar question on Slido. The question was, how do you know if your sampling strategy retrieves the vital interaction in the first layer? Shouldn't this depend on the data?
Okay. You may say the first challenger in the in our sampling strategy. How to say it? Actually, the idea is from the practice. We in experiment we try some sampling strategy because of it is time consuming if we do the sampling every layer. And we first try the only conduct the sampling strategy on the first half of layers. And we found this strategy is successful. And then we try to only use the first layer, and it is also effective.
Okay.
So we propose this.
An empirical finding. Okay, I got it. And one final question. So in your experimental setup, you say for evaluation, you have the target item and some randomly sampled negatives. So that's typically called sampled metrics. And there's been some work in RecSys by Rendell, by Pablo Castells, that says that the conclusions you can get using sampled metrics might not agree, or certainly it's making the task much easier. So I think you should probably see if your results hold using non-sampled evaluation metrics.
Yes, yes, I know what you are saying, and I admit this is one weakness of our experiment, and we may do the experiments in the 4 item list further.
Yeah.
Yes, yes.
Certainly, even last year there was evidence of
Yes.
different conclusions between sampled and unsampled metrics.
Yes, but I think the negative sampling strategy is general in the sequential recommendation task, and
I think it's fine for training. I think it's for evaluation that it's making the task much easier.
Yes, I understand.
Okay, let's thank the speaker. That was great.
Thanks.
Okay, so the final presentation of this session is a paper, an industry paper by Deezer Research, and it's entitled Track Mix Generation on Music Streaming Services Using Transformers. And I believe the presenter is Walid, yes.